So it's a pleasure to introduce our next speaker, Sam Ganzfried, who I had a chance to actually meet and chat with. And so I feel like I'm making new friends.
Yes, we just met yesterday. And so let me give a brief introduction to my background, actually. So I'm quite new to this field. My PhD was in computer science with my main research area focusing in computational game theory and more broadly in AI and optimization. Um, and I've worked on computing Nash equilibria and a variety and other solution concepts in a variety of different game classes in imperfect information, in multiplayer. During my PhD, I worked on computer poker, and I've worked on a lot of problems in national security as well. And recently, I've become very interested in cancer and disease treatment, and I'm hopefully can continue in this area. I am looking for new projects potentially where there's game theory models and people are looking for potentially improved algorithms. And so anyway, let me get into this talk. Um, so I'll be studying a game model that actually was developed by Kleshnina et al. And one of the authors, Joel Brown, in 2023. So they presented a Stackelberg evolutionary game model. Actually, it modeled a variety of different settings in biology, including fishery management. But one of them was cancer evolution, which is the model I'll be considering. And just to be clear, my contribution this model I'll be talking about is entirely their work. My only contribution here is going to be a technique for solving the model. So the model has two players. We have a follower and a leader. The leader is a physician who selects an amount of two different drugs, M1 and M2. And the follower is a cancer population, which is three cell types. It has type 0, which does not develop resistance to either drug. Type 1 develops resistance just to drug 1, and type 2 develops resistance just to drug 2. And so the follower is going to select two different quantities. It's going to select a population size for each type, x0, x1, x2. Also a trait, which is a real value in 0, 1 for each type, u0, u1, u2. These are all non-negative. The UIs are bounded in 0, 1. And these are implicitly going to be functions of time, so there's going to be a dynamic. It turns out this U0 doesn't end up appearing anywhere in the analysis, so it can be ignored. And so what are the two players trying to maximize? Well, for each cell type I, there is a fitness function GI that the follower is trying to maximize. And right now it's sort of abstract. I'll present a specific example. The dynamics basically X type I is going to grow in proportion to its fitness. And so we're going to be Stackelberg equilibrium. And in this equilibrium, we're going to have x dot equals 0. Now the follower is going to select UI that maximizes the GI. So U1 maximizes G1, U2 maximizes G2, and X0, X1, X2 are going to ensure that x dot is 0. Now the leader knows that the follower is going to behave in this way and subsequently select their actions as such. And so it's going to choose M1 and M2 to maximize this quality of life function Q. And so we can sort of compactly represent the entire problem we're trying to solve here, which is just what I just said. We're trying to maximize Q subject to being in equilibrium of the ecological dynamics, the UIs maximizing their fitness, and these non-negativity constraints and upper bound on the U's. And so in their paper, they proposed one example specific form for these functions for the G0, G1, G2, and Q, which has several hyperparameters. I'm not going to get too into this. This is their model and presumably is reasonable, but there could also be other models used here. So now I'm going to talk about the prior approach, which was paper, but there was a GitHub repository where they have code to generate some of the results used in one of their figures. And so I'm going to talk about the approach they use to try to calculate a Stackelberg equilibrium in this setting. And so the first thing they do is, assuming the UIs and the MIs are fixed, they're going to solve for the XIs that ensure that x dot is 0, that they have the equilibrium of the ecological dynamics. And this is just essentially going to be a system of three equations, three unknowns. It looks kind of messy, but it's just closed form analytical solution. And so this allows us to basically eliminate the x's from consideration and substitute in a function of the u's and the m's. Next, they are going to iterate over they're going to discretize the M1 and M2. Remember, these are the leader drug amounts, and they're going to discretize it so that they're multiples of 0.1 and that they're in the interval 0, 1. And go through each combination. And so for each value M1, M2, they're then going to look at this quantity here, which is the sum of the absolute values of the partial derivatives. And so now that M1 and M2 are fixed and they've substituted in for the X star, this quantity is just a function of the U1 and U2. And they're going to minimize this quantity, which is essentially, they're assuming essentially that the fitness functions are maximized at the point where the derivative is 0. And if both of them are simultaneously maximized where the derivative is 0, then minimizing this is going to simultaneously maximize G1 and G2. So they're going to do this, which is going to determine the optimal U1 and U2. They run this in MATLAB using this function fmin search bound, which with the u's bounded to be in 0, 1. And doing all this is going to give them the optimal U stars, and then they can plug these in and get the X stars. And so they're doing this for each combination of M1 and M2 in this discretized space. And so iterating over all of these 1 over h squared combinations. And for each one of these solutions, are going to say, what's the quality of life function, Q? And so this is going to determine, so the one that optimizes the Q is going to determine the optimal strategy for the leader, which is going to determine the overall Stackelberg equilibrium. And so this is the overall prior approach used. This is some pseudocode, but the sum of absolute values of the partial derivatives, and then picking the one that maximizes quality of life. And so what are some limitations of this approach? So one thing is that they're not explicitly checking that the X stars are biologically sensible, that they're non-negative. They're just plugging a closed form expression without checking this. Another issue is that, like I mentioned, they're discretizing these M1s to be multiples of 0.1 and divided by 1, which is, pretty coarse discretization. Another issue is that they are doing 1 over h squared separate optimizations, which may be costly depending on the procedure used. Another issue is that they're assuming that each GI is maximized and the partial derivative is 0, which is ignoring the potential the boundary case when the derivative is. And finally, they're using this function in MATLAB fmin search, which is not gradient based and actually is not guaranteed to find a local and certainly not a global one. So these are all potential limitations. And so here I present a new approach that is basically going to be a single bilinear quadratic program, which can be solved. So Garobi is a commercialization solver. And I believe 4 or 5 years ago, they released a non-convex bilinear solver, which has a guarantee of global optimality. Now, of course, it isn't going to scale to huge problems, but as we'll see here, this problem is well within its scope. And so to do this, we're going to introduce several auxiliary variables to obtain quadratic constraints. The only real challenge is that if you, in the example fitness functions we saw, there's the variables are in an exponent of e to the ui. And so Garobi has a function that does piecewise linear approximation of the exponential function. You can control the degree of approximation. But basically, this is the only element of approximation used. Other than that, this is an exact algorithm. And we're also going to use Lagrange multipliers and KKT optimality conditions to ensure that we can find boundary solutions in addition to interior solutions. So I don't expect you to look over all of this, but basically we can formulate the whole thing as one bilinear quadratic program. It might look kind of daunting, but it's actually, 20 or 30 constraints. If this were non-convex, I mean, you can easily solve problems with thousands of variables and thousands of constraints. So this is really not too bad. We'll see in terms of the running time in a slide or two. And so basically we formulate the whole thing as a single problem and solve it with Gurobi. And just to reiterate the advantages of this approach. So if you see here, we can explicitly model the non-negativity constraints for all the variables, make sure that they're non-zero, they're non-negative. We can allow AI not just to be restricted in 0, 1, and not just to be a multiple of 0.1. We're doing, we're not doing for h squared of them. We are explicitly using KKD conditions to ensure that we can find an optimal solution, whether it's boundary or interior. And this approach also has a guarantee finding the global optimum solution, of course, assuming it's able to solution that the problem's not too big. So we experimented. I used the hyperparameter values that were given in their GitHub repository. Presumably, these are reasonable values for the hyperparameters. And so the left column is going to be the results from the prior approach, and the right is from the new approach. And so one issue you can see immediately with the prior approach is that once they obtained a negative value, they feasible solution. You can't have a negative population.
Anyway, thank you so much. And actually, what was so delightful is you're now going to be my new best friend. Not just because you were able to identify that we had anti-individuals in our population, although negative cancer cells could be handy. Just what a brilliant evaluation. And I need to learn more about your programs. That was really great. But before I pick Sam's mind, does anybody have any questions?